Welcome to The Explainer. Today, we're digging into a pretty radical idea for building software. It's actually an old idea, but it promises something that feels almost impossible in modern development. Software that you can be absolutely certain just works.
Okay, so let's just dive right in with a scene that, well, it's probably going to feel a little too familiar if you've ever built software. You've got literally thousands of different files. You're juggling 20 different tools to manage them, and it's all just kind of loosely stitched together. There's no real single source of truth, is there? It's just a big collection of parts that we hope will all fit together.
In this complexity, right here, this is the real root of the problem. It creates this fog of uncertainty. We end up just crossing our fingers, hoping that the code that worked perfectly fine on our machine is going to behave the exact same way out there in production. We're not dealing with guarantees, we're dealing with approximations.
I mean, think about it. This modern file-based approach is a lot like a mechanic trying to build a car from 1,000 different parts, all arriving in separate deliveries. They're just hoping nothing got lost and that every single piece is the right one. It's a totally reactive process where we find the bugs after the car's already broken down.
But what if you could just step away from all that chaos? What if your entire system, your code, your data, even the tools you use to build it, was just one single living object? Something you could shape and modify with total confidence, like a sculptor.
Now, this isn't some futuristic sci-fi idea, not at all. It's actually a really powerful philosophy from the golden age of computing that is making a huge comeback. Why? Because the problems it solved way back then are the very same ones that are driving us crazy today.
So, back in the 80s, you had these legendary systems called Lisp machines that were built on this very idea. But then, as cheaper hardware came along, simpler file-based systems like Unix and C just kind of took over. And this whole powerful paradigm got almost lost. But today, it's being resurrected in modern systems like ISCV, which, by the way, stands for Image Integrated Smalltalk Component Vector.
Okay, so how does this whole rediscovered philosophy actually work? What in the world does it mean to develop inside a living image instead of just a folder full of static text files?
And this brings us to the absolute core principle of the whole thing. It completely flips the normal development process on its head. Instead of a bunch of scattered files being your source of truth, the running application itself is the source of truth. What this means is you're not doing that familiar dance of writing code in an editor, compiling it, then running it to see what happens. No, you are working directly inside the living, breathing, running system. Every change you make is immediate. Your editor, your debugger, and your application, they're all just different parts of the very same object.
Now, you might be thinking, wow, that sounds like it could get messy really fast. And you'd be right if it weren't for a really clever concept that makes this whole thing work without creating total chaos. It's all about absolute traceability, and it's achieved by keeping two perfectly parallel sets of records for every single change.
So on one side, you have the atomic history. Think of this as the machine's perfect granular audit trail. It automatically records every single definition, every little tweak. And then, on the other side, you have the human history. This is a clean, high-level story of the project, where you, the developer, get to group all those tiny atomic changes into meaningful milestones.
The workflow here is just so incredibly robust. You code directly inside the live image. The system is in the background automatically recording and auditing every single thing you do at an atomic level. Then, you get to curate those little changes into a human-readable commit message. And finally, and this is the absolute key, a brand new, perfect, clean image can be rebuilt from that curated history.
And that ability, right there, the ability to rebuild a perfect image, that's what leads to the ultimate payoff of this entire paradigm. It fundamentally changes how we think about deploying software.
We're moving away from the world of uncertainty, the world of recompiling a bunch of files and just hoping all the dependencies and libraries are exactly right. Instead, we have the certainty of perfectly reconstructing the exact same system with the exact same state every single time. We get to go from saying it should work to it will work.
I mean, just look at this. When you put these two ways of working side by side, the differences are just night and day, right? We're trading this scattered, reactive process for one that's completely integrated and proactive. Quality isn't something you check for later, it's literally built in by design. And traceability isn't just some vague log file, it's absolute and complete.
And that guarantee, that promise of exact reconstruction,
enables something pretty incredible. Zero, as in zero downtime for critical updates. You can literally modify a system while it's in production, reconstruct it from its own history, and deploy that update without ever taking the system offline.
So where does all this leave us? Well, this whole pursuit of certainty isn't just some abstract academic exercise. It's a direct solution to some of the biggest challenges we're facing today.
And the reason we need it now, more than ever, is because as our software systems have gotten more and more complex, the stakes have gotten so much higher. The consequences of failure aren't just an error message on a screen anymore.
I mean, think about the software that's running our flight control systems, our patient monitoring devices in hospitals, or the energy grids that power our cities. For these kinds of systems, hope is not a strategy. Failure is simply not an option.
Ultimately, it really all boils down to this. The image-oriented paradigm gives us a level of provable correctness that traditional file-based systems really struggle to even get close to. It delivers on that guarantee of exactly equal, and it is proven to work.
And that leaves us with a pretty provocative thought to chew on, doesn't it? In our huge rush for cheaper and simpler ways to develop, did we accidentally lose something absolutely essential along the way? And could it be that the key to building the truly reliable software of the future isn't found in some brand new technology, but in resurrecting a lost art?